Hello, my name is Kimberly Paredes, and the topic of this presentation is planar density of FCC crystallographic plane. FCC is face-centered cubic crystal structure and is common in metals like copper, aluminum, silver, gold, platinum, lead, and nickel. The unit cell, or simplest repeating unit of atoms, has a cubic geometry. Also, FCC has atoms located at all corners and all faces of the unit cell. Now, this is the 3D model of the FCC crystal structure. You can see that there are atoms at each of the corners and also one atom at each of the 6 faces of this cubic structure. You can see this model in more detail here. Now, for characteristics of FCC crystal structure, it has 4 atoms per unit cell. If we see the bottom sketch, there are half of the atom in each of the faces and 1/8 of the atom in all corners. The coordination number, or the number of neighboring atoms, is 12, and the atomic packing factor is 0.74, which is the highest packing of atoms possible for spheres of the same diameter. So this means that the structure is closely packed, and this stacking sequence is ABC, which means that the subsequent layers of atoms on top of the other will align in the spaces between atoms. Planar density can be defined as the number of atoms centered in a crystallographic plane per unit area of the plane. Its unit is reciprocal area, or meters to the power of -2, for example. Other ways to look at planar density is the measure of packing density of atoms in a crystal structure, or the portion of the plane that is occupied by atoms. This is the general formula for finding the planar density, which is the number of atoms that are centered on the plane divided by the area of the plane. Now you may wonder, what is the point of knowing planar density? Well, planar density is important for understanding the process of slip that results in plastic deformation in metals. So a slip occurs on the most densely packed crystallographic planes. Thus, knowing the planar density will allow us to determine if a plane is more susceptible to slip. Deformation, in turn, will alter the material structure and consequently its mechanical properties, which can affect the performance of our material. This is the problem statement. Calculate the planar density for the FCC 111 plane for aluminum metal, given that the atomic radius for aluminum is 0.143 nanometers. So this is our crystal structure. We can look at this in more detail here. We can see our FCC crystal structure and also the plane, the 111 plane. It touches the Z plane at 1, the X, and the Y axis at 1. You can see the plane in more detail. Now, let's go back to the problem. This is a 2D repeated unit for the 111 plane. This represents the portion of FCC 111 plane within a unit cell. We can see that each side of the triangle of this plane has 4 radius. So now to the solution. As we see in the previous slide, we have a total of 2 atoms. We have 1 sixth of an atom in each of the plane's corners, and 3 half atoms for a total of 2 atoms. So we have 2 atoms centered on 1, 1, 1 plane. Now, the area for a triangle, which is how our plane looks like, is 1/2 times base times height. Now, we need the height in terms of radius. So we use the Pythagorean theorem, and we get that 2r, if we look at half of the triangle, we can see that the base is 1/2 of the total side of the triangle. So if each side is 4r, then half of that would be 2r. So 2r squared plus h squared, which is height, equals to 4r squared, which is the hypotenuse in this triangle. So if we perform these calculations, we get that height, or h, equals to r square root of 12. And we can conclude that the height is radius times the square root of 12, and base is 4 times radius. If we put this all together in the area for the triangle or the plane, we get 2r squared times the square root of 12. So we can conclude from this that the planar density for the 1, 1, 1 plane for FCC will be 2 atoms over 2r squared to the square root of 12, which is the area of the plane. Why do we choose 2 atoms? Because there are 2 atoms centered on the plane. And then this will be equal to 1 over the radius squared times the square root of 12. Finally, we can get the solution that the planar density of the 1, 1, 1 plane for FCC in aluminum is 1 over 0.143 squared times the square root of 12, which gives us 14.1 nanometers to the power of -2, which is also equal to 1.41 times 10 to the power of 19 meters to the power of -2, or reciprocal meters squared. Thank you for your attention. That was the presentation. Of how to calculate the planar density for a crystallographic plane in FCC crystal structure.